Welcome to the deep dive. This is where we take your sources, pull out the really key insights, and basically give you a shortcut to being genuinely well informed. Today, we're diving into something huge and frankly pretty critical: artificial intelligence, specifically how it's getting woven into decision making everywhere, especially in banking. We're going to be unpacking bias and fairness in AI and looking at the real world consequences. Think about someone, let's call her Sarah, a really sharp entrepreneur applying for a business loan, and AI might turn her down. We want to get into why that could happen and how we can build systems that are actually fair to people like Sarah.
That's exactly right. Our mission today is to really unpack this idea of responsible AI. And it's more than just a buzzword. It absolutely demands fairness, explainability, the AI showing its homework, telling you why it made a decision, and human oversight. That last one's crucial, having a person who can step in, especially for big decisions. We'll explore why tackling bias is just fundamental for companies today. It's about aligning with AI regulations, yes, but also with basic human rights standards, particularly when decisions are automated. You might think AI is objective by nature, but, well, we're going to see that's often a big misconception.
Okay, yeah, let's jump right into that misconception. I think a lot of us assume, algorithms mean more objective decisions. Machines don't have feelings, right? But you're saying that belief is often misguided. So why do these machine learning algorithms fall short? Where does the subjectivity come in?
Well, the heart of the issue is that bias isn't really an AI problem initially. It's a human society problem. We create the data. And our societal biases, conscious or not, get embedded right into that data. So the algorithms learn from this biased data, which means they can end up making unfair decisions, just like humans can. Recent studies have really hammered this home AI can inadvertently cause harm, especially in really critical areas like hiring or, like you said, loan applications. These decisions change lives. So prioritizing ethical checks, ethical improvements in these systems, it's just paramount.
Okay, so if the bias is sort of baked into the data from the start, how does that actually ripple through, like through the whole process of building and using an AI? Where does it pop up?
It could pop up pretty much everywhere, actually.
Yeah.
Right from data collection through model development all the way to deployment. It's tricky because it's often hard for the people building these things to even spot where the issues are. The sources we're looking at make a useful distinction, kind of between philosophical and technical views of bias. It gives us a good frame. So from a, let's say, philosophical angle, you've got things like historical bias. Think of this as warping the difference between someone's potential and how we try to measure that potential. It sort of distorts the ideal into a construct we observe. So maybe Sarah's community was historically underserved by banks, that history could bias the potential the AI sees, and then measurement bias comes in and twists that construct even further into what we actually see in the data. Maybe the credit score used doesn't really capture Sarah's actual financial resilience.
Okay, so that's the sort of deeper societal level bias. What about the technical side? How does it manifest there?
Right. So from a technical viewpoint, you start with a world already shaped by that historical bias. Then, first up, you might get representation bias. This happens when your training data just isn't representative of the real-world population. Maybe Sarah's demographic group, say recent immigrants, is underrepresented in the loan data the AI learns from.
So the AI just doesn't learn properly for people like her.
Exactly. Then there's measurement bias again, technically speaking, using a proxy variable, like that credit score for financial responsibility, and that proxy happens to correlate unfairly with sensitive things like race or gender. Then you get algorithmic bias itself, bias introduced during the model development. Could be aggregation bias, like using one single model for diverse groups when they might need different approaches. Or learning bias from how the model is optimized, what it's told is good. Or even evaluation bias, testing the model against benchmarks that aren't appropriate or fair themselves. And finally, there's deployment bias. This is about how humans use the AI's predictions. Maybe the system was meant to be fully automated, but people use it just to inform their own decisions, and they end up reinforcing the biases that AI picked up.
Wow, okay. That's a lot of places for things to go wrong. It sounds incredibly complex, almost like navigating a hidden minefield. How do practitioners even begin to get a handle on this, to investigate these different bias types systematically?
Yeah, it's a huge challenge. And that's where tools like bias on demand come into the picture. It's a framework that lets researchers basically create synthetic data. But the key is they can generate data with specific types of bias deliberately built in.
Ah, so you can create controlled experiments.
Precisely. It lets you study situations you just wouldn't find easily in real-world data, and you have exact control over how the data was generated. This kind of capability is really important for building trust, and for promoting the development of genuinely responsible AI systems. It helps us see the bias more clearly so we can address it.
Okay, so tools like bias on demand help us understand the problem. But with bias potentially everywhere, how do we even define what fair means for an AI? I heard something about there being 21 definitions of fairness. That sounds, frankly, overwhelming.
It is a bit overwhelming,
Mhm.
and it really highlights that fairness isn't one single thing. It's multifaceted, full of nuances, and sometimes the definitions even conflict with each other. But we can broadly categorize them. We often talk about group fairness versus individual fairness. And there's also a distinction between observational fairness and causality-based fairness.
Okay, let's break that down. Group fairness.
Right. Group fairness is about achieving some kind of statistical parity across different groups, defined by protected attributes like gender, ethnicity, age, and so on. Let's stick with Sarah's loan example. One type is demographic parity, DP, sometimes called statistical parity or independence. Basically, it means the rate of positive outcomes, like getting a loan, should be roughly the same for men and women, or across different ethnic groups.
So equal approval rates across the board.
Essentially, yes. It often means actively working against historical trends, changing the status quo. Then you have others, like predictive equality. This focuses on making sure the false positive rates are equal. So the rate at which the AI wrongly predicts someone will default on a loan should be similar for all groups. Equality of opportunity, EO, looks at the false negative rate. If someone should qualify for a loan based on their merits, the model shouldn't misidentify them more often in one group than another.
Making sure good candidates aren't overlooked unfairly.
Exactly. And there's predictive parity, PP, which says the model's precision, its accuracy when it does predict a positive outcome, should be the same across groups.
Okay, that's group fairness. What about individual fairness?
Individual fairness is simpler conceptually. It's the principle that similar individuals should get similar outcomes, regardless of what group they belong to. So if Sarah and, say, David have identical financial profiles, loan histories, everything relevant, their loan decisions should be similar, even if they differ on a protected characteristic like ethnicity.
Makes intuitive sense. And the causality-based one.
Those are trying to dig deeper. Counterfactual fairness, CFF,
Yeah.
and path-specific, counterfactual fairness, PCFF, try to prevent unfair causal links. They ask, would the decision have been different if this sensitive attribute had been different, holding other things constant? It's about blocking unfair causal pathways.
Okay, so we have all these different ways to measure fairness. Group, individual, causal. Can you actually satisfy all of them at the same time? Because it feels like some might pull in different directions.
That's a really critical point. And the short answer is no, generally you can't. The sources are very clear about these incompatibilities. For instance, a classic one is that if the thing you're trying to predict, like loan repayment, isn't itself statistically independent of the sensitive attribute in the real world,
which is often the case due to historical factors.
right, then you usually cannot simultaneously achieve both separation-type fairness, like equality of opportunity, and independence-type fairness, like demographic parity. It means in most real-world situations like lending, we face these fundamental trade-offs. There's no perfect solution. We have to make very deliberate, ethical choices about which aspects of fairness are most important in a specific context. For Sarah's loan, do we prioritize equal opportunity for qualified applicants or overall equal approval rates? It's a tough balancing act.
That does sound like a heavy ethical choice, not just a technical one. So given we have to make these trade-offs, what are the practical strategies? How do we actually do bias mitigation in AI systems?
There are three main buckets of approaches, usually applied at different stages of the AI pipeline. First, pre-processing mitigation. This involves changing the training data before the model learns from it.
So fixing the data itself.
Kind of. Techniques include things like massaging, which might mean carefully altering some outcome labels in the training data to counteract historical discrimination, or reweighing, giving more importance to data points from underrepresented groups, or sampling, which involves either oversampling the minority group or undersampling the majority group to get a more balanced data set, maybe ensuring enough examples like Sarah's are included.
Okay, pre-processing. What's next?
Second is in-processing mitigation. This means modifying the learning algorithm itself during training. You essentially build fairness metrics right into the model's objective function, so it learns to be accurate and fair simultaneously. Adversarial learning is one technique used here.
So you're teaching the model to be fair as it learns.
Exactly. And the third approach is post-processing mitigation. This happens after the model is already trained. You take the model's raw outputs, its predictions or scores, and adjust them. Often this involves setting different decision thresholds for different groups to achieve a fairness goal.
Like adjusting Sarah's required score slightly.
Potentially, yes, based on achieving a specific fairness metric across groups. And finally, there are causal methods. These can sometimes fit into pre, in, or post-processing, but their goal is specifically to ensure counterfactually fair outcomes by trying to block those unfair causal pathways we mentioned.
Okay, three main strategies. Pre, in, and post-processing, plus causal methods. What are the pros and cons? Why choose one over the others?
Well, pre and post-processing are often seen as maybe easier to implement. You don't necessarily have to tinker with the core machine learning model, which can be complex. But the downside is they might offer less direct control over the fairness-accuracy trade-off. They can sometimes have weird downstream effects, maybe legal implications, or make the final model harder to interpret.
And in processing?
In processing gives you more direct control during training, so it can be more tailored, but it often requires modifying specific algorithms, so it might be less generalizable, less easy to apply across different types of models. It really depends on the specific needs and constraints of the project.
It definitely sounds like a complex decision for data scientists. Are there practical tools out there designed to help navigate this, to actually implement these strategies in the real world?
Absolutely. And that's crucial. We actually developed a toolkit called BFair. It's designed precisely to help data scientists in real use cases, like the credit lending scenario at Intesa Sanpaolo we mentioned. BFair handles the whole workflow, detecting bias in the data and the model's predictions, implementing various mitigation strategies in post-processing, evaluating the results, and really helping visualize those trade-offs between model performance and fairness.
So it makes the process more manageable?
Exactly. For instance, in that Intesa Sanpaolo project with 250,000 personal loan applications, BFair was used to look at bias linked to things like citizenship. And what we found, which isn't surprising but is important, is that just applying standard machine learning models often amplify the existing biases in the data. It really underscores why active fairness interventions using tools like BFair are so critical. They help ensure people like Sarah aren't unfairly penalized by the algorithm.
Okay, BFair helps manage mitigation and trade-offs. But one concern with AI is often the black box problem. Can we get solutions that are not only fair but also transparent, so we can actually understand why a decision was made?
Yes, transparency is hugely important, especially in regulated sectors like banking. And that brings us to another tool we developed, FF-Tree. It stands for Flexible Fairness-Aware Tree. You see, many earlier mitigation strategies had limitations. They might only work for one specific definition of fairness, or struggle if you have multiple sensitive attributes like race and gender.
Right.
Or they might only apply to certain types of machine learning models. And crucially, as you said, they were often black boxes. You couldn't easily see the decision logic.
So how is FF-Tree different? What makes it transparent and flexible?
FF-Tree builds on classical decision trees, which are naturally quite interpretable. But it enhances them by explicitly incorporating fairness constraints when it decides how to split the data at each node. Its key features are 1. Flexibility. You can choose from a wide range of fairness criteria, disparate impact, disparate mistreatment, many others. You can even combine multiple fairness definitions or mitigate across several sensitive groups simultaneously.
Like dealing with potential bias based on both gender and race at the same time.
Exactly. We showed this working on the well-known adult data set.
Yeah.
And you can set a specific fairness target level as an input, which is great for meeting business or regulatory requirements. 2. Transparency. Because it is a decision tree, its logic is inherently transparent. You can literally trace the path to a decision. The fairness rules aren't just an afterthought. They're built into the structure of the tree itself.
So each split in the tree is checked for fairness.
Right. It searches for the split that gives the best information gain while also satisfying the chosen fairness constraint. This means the whole tree, even if you simplify it, remains fair by design. Our experiments show its performance is right up there with other fair tree methods, but with this added flexibility and transparency, it lets you build a model that could explain clearly why Sarah got her loan and show that the decision process was fair.
That's powerful. Okay, so we have tools like BFair and FF-Tree for building and assessing fair systems now. But AI models aren't static, right? They operate over time, data changes, the world changes. How do we ensure fairness isn't just a snapshot, but something that persists?
That's a really crucial and frankly cutting-edge challenge. It's not enough to just build a fair model once. We need a continuous approach. We propose a roadmap for fairness in machine learning projects, especially for banking. It involves 6 key stages and requires deep collaboration across different teams, data scientists, ethicists, legal experts, business units.
6 stages. What are they?
1. Regulatory aspects. Constantly keeping up with evolving laws like the EU AI Act or the US AI Bill of Rights. These define sensitive attributes and often shape fairness expectations. 2. Data set assessment. Really digging into the data, understanding potential correlations between features and sensitive attributes, looking for historical biases. 3. Choice of fairness metrics. This is critical. Acknowledging there's no single right metric and making conscious, documented choices based on ethical and legal assumptions and the specific context.
The trade-offs we talked about.
Exactly. 4. Bias mitigation. Selecting and implementing the appropriate strategies pre, in, or post-processing. 5. Comparison and evaluation. Rigorously testing the effectiveness of the mitigation and understanding the performance impact. And 6. Crucially, monitoring fairness. Establishing robust systems to track fairness metrics over time, detect drift, prevent biases from creeping back in, and alert when thresholds are breached.
That monitoring piece seems key for the long term. But going back to stage 3, choosing the metrics. If different people, different stakeholders, have fundamentally different views on what fair even means, how do you make that choice? It sounds like you need an ethical compass before you even pick the metric.
You absolutely do, and that's a huge hurdle. This is where another tool, Fairview, comes into play. Fairview is designed to help users navigate these ethical choices. It supports selecting an underlying ethical framework or worldview when you're developing an AI system. It uses AI itself, evaluative AI, and contrastive explanations. Importantly, it doesn't just recommend a worldview. Instead, it provides evidence for and against different moral frameworks based on the data.
So it helps you reason through the ethics.
Precisely. It helps clarify the situation. For example, it helps distinguish direct discrimination, where a sensitive attribute like race was explicitly used in the decision-making process.
Like asking for race on a loan form and using it.
Right. Versus indirect discrimination, where even if the sensitive attribute wasn't used directly, other patterns in the data correlate with it and lead to unfair outcomes anyway. Fairview works in 3 steps. First, trace. It trains separate decision trees for each sensitive group to understand the logic driving their outcomes. Second, G-contrast explanation. It compares the decision rules between groups to pinpoint why outcomes might differ. Are the factors different, or are the same factors weighed differently? And third, worldview evaluation. Based on those differences, it provides evidence supporting one of 2 main worldviews. One is we are all equal in potential space, WAPS, which assumes an ideal state of equality and that observed differences are likely due to bias and should be corrected for. The other is what you see is what you get, YSIYG, which takes observed differences in the data as potentially legitimate grounds for different treatments or outcomes.
So it frames the ethical debate based on the data itself.
Exactly. It helps practitioners see, for example, if the pattern suggests historical bias, supporting WEDI APs, or perhaps real current differences in risk profiles, potentially supporting WYSIYG, though carefully. It helps make that foundational ethical choice more explicit and data-informed. It helps the bank decide. Was Sarah's initial profile seemingly riskier due to systemic disadvantage or current factors the bank deems legitimate? Fairview provides evidence to inform that choice.
That's incredibly helpful for setting the initial ethical direction. But let's go back to the long-term problem. Systems change, data drifts. How do we actually maintain fairness over time? How do we make sure a system deemed fair today doesn't become unfair next year? This seems vital for people like Sarah, whose circumstances might improve over time.
This is arguably one of the toughest, most dynamic parts of responsible AI. Let's take that bank example again. Imagine the bank implemented some fairness measures, but they noticed that clients from disadvantaged groups like Sarah's community, who maybe struggled initially, still show up as bad clients in the data years later, purely based on financial status, even if the initial direct bias was removed. There's this persistent life bias, a cycle that's hard to break. The bank genuinely wants to ensure its system doesn't perpetuate this.
So initial fairness fixes aren't enough.
Often, no. We looked at this using real data from Intesa São Paulo, a massive data set, 800,000 loan documents from 2016 to 2019. We found that standard mitigation techniques, while maybe effective right after training, often fail to maintain fairness goals like demographic parity, even just 1 year later.
The fairness decays over time.
Yes. And this decay gets worse if there are conditioned shocks in the data, like, say, an economic downturn disproportionately affecting the income of one specific group. So our idea was to aim for long-term convergence. We proposed a dynamic approach, train an individual fair model focused on treating similar individuals similarly, Then use its predictions to continuously update a separate group mitigation model designed to maintain the group fairness target.
A two-pronged approach.
Kind of, yeah. And this combined strategy performed better over time, maintaining the desired group fairness level more consistently. But how do you monitor this? That's where FairX comes in. It's a monitoring strategy using explainable AI, specifically SHE values, Shapley values.
Okay, what do SAP values tell us here?
Think of SHE values as explaining why an AI made a specific decision for one person, breaking down how much each factor contributed. For FairX, we use them to see the marginal contribution assigned by the mitigation model to sensitive attributes. Are protected characteristics like gender or ethnicity still implicitly driving decisions, even after fairness interventions?
So you're looking at how much the fix relies on knowing someone's group.
Exactly. If, after retraining the model over time, the SHAP values associated with sensitive attributes decrease, it's a good sign. It suggests the model is achieving group fairness with less reliant on discriminating at the individual level based on those attributes.
A sign of genuine long-term improvement.
Ideally, yes. Though interestingly, our experiments also show that sometimes, due to broader economic shifts, individual discrimination measured by SHAP could actually increase even while group fairness was being maintained.
Wow, so it's a constant balancing act.
It absolutely is. It highlights the need for continuous vigilance, monitoring both group and individual fairness aspects, and being ready to recalibrate as the world changes.
This has been such an incredibly insightful deep dive. It's clear that the simple promise of AI objectivity, well, it's often just a mirage because of biases deeply embedded in our data and society. We've navigated the really complex landscape of fairness definitions, looked at practical ways to tackle bias with tools like Be Fair for management and FF3 for transparency, and stressed the absolute need for a long-term view, a roadmap.
And we saw how newer tools like Fairview can help us grapple with the underlying ethical choices, while FairX provides a way to monitor fairness over time, making sure our systems stay responsible. This whole journey really shows that building trust in AI isn't just about technical skill. It's fundamentally about understanding the deep societal and ethical implications for real people, like Sarah in our example.
So what does this all mean for you listening? When you encounter an AI making a decision that affects you maybe alone, a job application, even a recommendation online, take a moment. Think about the hidden layers. Could historical patterns be influencing this? What about the data it learned from? How might the algorithm's design itself be shaping the outcome? What ethical rules do you think should guide it? And how would you check if it stays fair over time?
Yeah, the pursuit of responsible AI isn't a destination. It's definitely an ongoing process. It demands constant critical thinking from all of us, real collaboration between different fields, and a deep commitment. A commitment to ensuring these powerful AI systems are not just effective tools, but tools that are genuinely equitable and fair. That's how we foster trust and unlock the real promise of AI for everyone in society.